Hello! In this video I'm going to be going over intermolecular forces. So far when we talk about bonding, we've been talking about the intramolecular forces, the forces that bring atoms together to form various molecules. So we talked about ionic bonding and covalent bonding, two types of covalent bonding, that being polar and nonpolar. Polar bonding, or polar covalent, being the electrons are being unequally shared, whereas nonpolar covalent is the electrons are being equally shared because of an relatively equal electronegativity value of the various atoms that make up the molecule. Intermolecular forces is looking at the forces between molecules that cause them to stick together. So why is a substance a liquid instead of a solid, or a solid instead of a gas? It has to do with intermolecular forces. So if you were to be given the question, what has the strongest intermolecular forces, solid, liquid, or gas? The correct answer would be solid, because they are sticking so close together. And then a liquid has a little bit weaker intermolecular forces, and a gas even weaker yet, because they're not even trying to connect or touch each other, those gas molecules. There are three main intermolecular forces, one being dispersion, the other being dipole-dipole, and the third being a type of dipole-dipole, which is hydrogen bonding. So we'll start with dispersion forces. It's either called London dispersion forces, van der Waals forces, or dispersion forces, all the same thing, and they are weak forces that result from temporary shifts in the density of electrons in the electron clouds, and this is the weakest intermolecular force. So basically, just as this picture shows, you have a partial positive and a partial negative on this molecule based off of the electronegativity. And this dispersion force is found in all molecules, even in nonpolar substances where you have no partial positive or partial negative because it's an equal value. However, even those molecules do have a partial positive and a partial negative just by random. Because randomly you might have more electrons in one spot and less electrons in another spot, and blip, for a very small amount of time you'll have a partial positive, partial negative, and that can then connect to another molecule that happens to have a partial positive and partial negative. So, and then they stick together in these intermolecular bonds, so to say. So dispersion forces are the weakest of all intermolecular forces. All bonds or compounds have them, whether it be nonpolar, polar, or even ionic. Alright, the next type is dipole-dipole. So this one is, just as it says, it has dipole, two poles. It has a partial and it has a negative. So it's a partial positive, partial negative. It has to do with unequal sharing of electrons. This is found in polar molecules. You're going to have a dipole moment, meaning the electrons are going to hang out by the electronegative, the one that's more electronegative, more so, less by the one that is not as electronegative. And it forms this partial negative where the electrons are, and this partial positive where the electrons aren't around as much. So it's kind of like the same thing with an ionic bond, only an ionic bond it's permanent, where you have a plus charge and a minus charge. This is a weak version of an ionic bond where they're just partial, positive, minus. And then what's going to happen is the partial negative of one molecule will stick to the partial positive of another molecule, forming this dipole-dipole attraction, because this has two poles and this has two poles, hence the dipole-dipole moment, this intermolecular force right there. Will you find a dipole-dipole force in nonpolar substances? The answer is no, you will not. You'll only see dispersion forces. But in a polar covalent substance, you will see dipole-dipole intermolecular forces along with dispersion forces. And last but not least, we have hydrogen bonding, which is a type of dipole-dipole moment, or a dipole-dipole intermolecular force. The only difference is it's a dipole-dipole force on steroids. So it's the most extreme inversions. It has to do with a huge electronegativity difference, and basically it works with the FON group, fluorine, oxygen, and nitrogen. So if you have fluorine, oxygen, or nitrogen, and this molecule is polar, and you have a hydrogen in that molecule, then it is hydrogen bonding. You do not have F, O, or N, it's just dipole-dipole. So water is an example. You have hydrogen with a partial positive and oxygen of another molecule with a partial negative. So you have this H to O. O is F, fluorine, oxygen, or nitrogen is part of that FON group. So this is definitely hydrogen bonding. If this was an N right here, or an F, it would also be hydrogen bonding, but if it was an S, it would not be. Alright, let's have some fun with some examples. So we got this nice little worksheet right here. It says identify the intermolecular force present in samples of the following substance. Alright, so we have SO2, and in order to do this we need to have a strong knowledge of how to draw Lewis dot structures. So we have sulfur, it's in column 6A or 16, so it has 6 outer electrons. But let's do it that other way, where we have 6 electrons for sulfur plus 6 for oxygens, because it's in the same column but there's 2 of them. 6 times 2 is 12 plus 6 is 18. So we're going to have at least one bond to each sulfur oxygen. That's 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Anything left over, 17, 18 goes on the center. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6. We're going to have a double bond. It looks like resonance is happening. So that's going to be one structure. And, you know, technically I would draw both structures, but for this moment, in this situation, we're not looking at drawing a Lewis dot structure. We're just looking at what's the intermolecular force present. So we gotta look at this. Left and right. Is it symmetrical? The answer is no, it's not symmetrical. And if you say no to that question, is it symmetrical? Then it is polar. So this guy is polar. If it is polar, it definitely has dispersion forces. All have dispersion. So we're going to put dispersion. And then we have to ask ourselves, does it have a dipole moment? And we have to say yes, because it's polar. All polar substances have a dipole moment. So therefore, dipole, dipole. And then the third question is there hydrogen bonding? Is there hydrogen that could bond with fluorine, oxygen, or nitrogen? And in this case, we would say no, there is not, because if we had another sulfur, there's no hydrogen around, so there could not be any hydrogen bonding. So this one is just dispersion and dipole, dipole. Alright, doing another one, H2O. This one's a classic. We have oxygen is 6, hydrogen is 2, that's 8. 2, 4, hydrogen can't have any more. 5, 6, 7, 8. Is this symmetrical? This way it is, but is it symmetrical this way? The answer is no. So it is not symmetrical, therefore this guy is polar. Does it have dispersion? Yes. Everything has dispersion. Does it have dipole-dipole? The answer is yes, because it's polar. It does have a dipole moment, partial positive, partial negative. And then is it hydrogen bonding? So we have oxygen and there's hydrogen. So FON, FON group, oxygen is part of that, so there is hydrogen bonding. So H bonding. And if we drew another water molecule, you'd have this intermolecular force between this partial negative oxygen and this partial positive hydrogen. And that is what we're looking at. We're not looking at the forces within this molecule, we're looking between the various H2O molecules. And it is dispersion, dipole-dipole, and H bonding. Alright, doing another example, we have CH2Cl2. Written like this because we have 2 and 2, so they're paired up. And is this symmetrical the way it is written? The answer is no. So therefore it's polar. And if this is polar, we do have dispersion. And if it's polar, then we do have dipole. We do have hydrogen, so maybe it's hydrogen bonding too. But FON, Fon group, don't have any of those. So therefore, it's just dispersion and polar. Alright, let's skip to PCl3. Got Cl, Cl, Cl. It's going to be written like that, PCl3. Is it symmetrical? The answer is no, so therefore it's polar. And if it's polar, it has dispersion and it has dipole. Does it have hydrogen? There's no hydrogen in the molecule, so right away, no, cannot have hydrogen bonding. It's just dipole, and dispersion. Alright, let's do one last one. We've got Cl2. Looks like this. Cut in half. Is it symmetrical? Yes. So it does have dispersion. But is it polar or nonpolar? The answer is it's nonpolar. Therefore, all it has is dispersion forces. And that's intermolecular forces. Pretty fun. It's a concept that will pop up, explains a lot of things, and if you take IB chemistry, it is important to know.